Okay, good morning everyone. Today we are going to discuss, you guessed it right. Today we are going to discuss the last topic of carboxylic acid, that is acidic nature of carboxylic acid. Carboxylic acids, they claim that we are acidic in nature. Can you guess why they can claim that they are acidic in nature? Because they have the word acid in their name. So acidic nature of carboxylic acid. So what happens is the carboxylic acid is there, it has the OH bond which is polar due to electronegativity difference, and the polar bond can ionize like this slightly to give out H plus ions. The hydrogen comes out as H plus acidic hydrogen, and you get a conjugate base. After giving H plus, it will become a conjugate base called the carboxylate ion. The conjugate base is formed, that is called carboxylate ion. As it is evident from the equilibrium sign, it is not, organic acids are not very strong acids. They are not as strong as inorganic acids like HCl, sulfuric acid, and nitric acid. So the reaction will not go to the completion. So carboxylic acid gives out H plus ions because they have polar OH bond which can ionize to give you H plus ions. Now carboxylic acid has a resonance, but we'll just prove it. It is less resonance stabilized. Less in comparison to what? To the carboxylate ion. So it is less resonance stabilized. Whereas carboxylate ion, the conjugate base which is formed, is comparatively more resonance stabilized. We are going to prove it. So we can also say that carboxylic acid, which is less resonance stabilized, will try to convert into carboxylate ion which is more resonance stabilized, and in the process it gives out H plus ions. Now since this is a reversible reaction in equilibrium, we can write equilibrium constant for the reaction. This is Ka, dissociation or ionization constant of an acid. Equilibrium constant is concentration of product divided by the concentration of the reactant. You do know that if the value of K is more, acidic nature will be more. So if they ask you to compare or arrange in the increasing order of K, basically they ask you to arrange the compounds in the increasing order of acidic nature. We can define one more factor called pK, that is minus log of Ka. And as it happened in pKb, this is also inversely proportional to acidic strength. Meaning by, if you have to arrange the compounds in the increasing order of pK, that means decreasing order of the acidic strength. So we just write down this thing, that carboxylic acid is acidic in nature. Carboxylic acid is acidic in nature. Acidic in nature. As it readily gives out, readily gives out H plus ions, forming highly resonance stabilized, highly resonance stabilized carboxylate ion, highly resonance stabilized carboxylate ion. We are going to prove it within few seconds, that why carboxylate ion is more stable as compared to the carboxylic acid. So let's proceed further. Let us compare the resonance stability of the carboxylic acid and the carboxylate ion. Let's prove why carboxylic acid is comparatively less stable as compared to the resonance stability of the carboxylate ion. Let's draw the resonating structures. If you draw the resonating structure of carboxylic acid, number one, they will not look alike, and they will have a charge separation. Charge separation means they will have a negative charge separate and a positive charge separate. And any structures where there is negative and positive separated out, their resonance stability is very, very less. So the other one will be like this, and the structures are not equivalent. Anybody who has got resonating structures which are equivalent are having a very, very high stability. So there is a charge separation. If you see the resonating structure of carboxylate ion, the first point is that they look alike, they are identical. As I will draw, you will come to know why they are identical, why do they look alike. And secondly, that they will have no charge separation. They have no charge separation. They don't have any charge separation. So because of these two reasons, these are more stable as compared to this one. So we can write down that why carboxylate ion is more resonance stabilized as compared to the phenoxyl ion. So we can write down carboxylate ion resonating structures. Carboxylate ion resonating structures. Carboxylate ion resonating structures are more resonance stabilized. Carboxylate ion resonating structures are more stabilized. Or we can write carboxylate ion is more resonance stabilized. More resonance stabilized in comparison to carboxylic acid. That's why carboxylic acid is changing into something which is more stable, more resonance stable. So we are writing. The first reason is resonating structures of carboxylate ion are equivalent. Resonating structures of carboxylate ion are equivalent. Carboxylate ion are equivalent. They are equivalent. Secondly, resonating structure of carboxylate ion, resonating structure of the carboxylate ion have no charge separation. Carboxylate ion has no charge separation, has no charge separation, which is there in the case of carboxylic acid. So basically carboxylic acid is acidic in nature because the conjugate base of carboxylic acid has got or is more resonance stabilized. Now let us see what is the effect of the groups. If you put some groups on carboxylic acid, how does it changes its acidic nature? Already we have done in the case of acidic nature of phenol and alcohol. If you put electron withdrawing groups, the acidic nature increases. If you put electron donating group, the acidic nature decreases. Basically what happens if you put in this molecule electron withdrawing group, the stability of carboxylate ion will increase further, because if you put an electron withdrawing groups over here, if the electron withdrawing group is present over here, it is going to pull away the negative charge like this. It is going to disperse the negative charge, and if the charge gets dispersed or pulled away, or the magnitude of the charge decreases, the stability will increase. So electron withdrawing group is going to pull away the negative charge of carboxylate ion, making it more stable. And if this is more stable, it will be readily formed or acidic nature will increase. So basically, electron withdrawing group increase the acidic nature of carboxylate ion by making carboxylate ion even more stable. So more the stability of carboxylate ion, more will be the acidic nature of carboxylic acid. So what we are now discussing is nothing but the effect of substituents or the groups, effect of the substituents or the groups on acidic nature of carboxylic acid, on the acidic nature of carboxylic acid. We are discussing the effect of the acidic nature or the groups on the acidic nature of carboxylic acid, on the acidic nature of the carboxylic acid, on the carboxylic acid. So as I told you just now that electron withdrawing groups namely your nitro group, your halogens. If you put all these groups, the acidic nature will increase. They stabilize the carboxylate ion. They stabilize the carboxylate ion. They stabilize the carboxylate ion, and acidic nature will increase. Acidic nature will increase as they will disperse the negative charge of carboxylate ion, make it more stable, and the acidic nature will increase. If you put electron donating groups like R group, they will destabilize, make it less stable. They will destabilize the carboxylate ion, destabilize the carboxylate ion, and with the result acidic nature decreases. Acidic nature will decrease. So let's see with an example how does the substance funda work. Withdrawing group increases and donating group decreases. So let us compare the acidic nature of the following acids. We are comparing the acidic nature of the following acids. Let's compare the acidic nature of, first of all, formic acid and acetic acid. In acetic acid, there is a CH3 group, strong plus effect, electron donating group. So naturally acidic nature will be less. So formic acid is better as compared to acetic acid. Now let us see this one. We have got fluoroacetic acid having fluorine. We have got chloroacetic acid having chlorine. We have got bromoacetic acid having bromine. We have got iodoacetic acid having iodine. Acidic nature of fluorine wala will be better than chlorine wala, then bromine wala, then iodine wala because of the electronegativity. This is a better withdrawing group, lesser, even lesser. Now let's see this example. We have trifluoroacetic acid. We have trichloroacetic acid, or we can have difluoroacetic acid. Difluoroacetic acid. We can have fluoroacetic acid, and we can have only acetic acid. So the one having 3 withdrawing group is going to be better than 2, then 1, and then none. If you compare the acidic nature of this one, let's say we have got propanoic acid and we have got ethanoic acid. More the carbon atom in the alkyl group, more is the plus I effect. So this will be stronger. It has only 1 carbon atom, so plus I effect is less. In this case there are 2 R group, so plus I effect is stronger, so acidic nature will be less. Electron donating power, electron donating group, the power is more. Naturally more number of carbon atom, more is the donating power. Now let us see some more examples. Let's compare the acidic nature of formic acid, benzoic acid. We'll compare it with benzoic acid. We'll compare it with acetic acid. Let's see out of the 3 which is more acidic, which is less acidic, even less acidic, and so on and so forth. You will find formic acid is going to be stronger than benzoic than acetic acid. Why? In acetic acid we have a strong electron donating group. In benzoic acid what is there is the benzene actually gives electron due to resonance. It's giving electron due to resonance. It pulls away the electron due to minus I effect. It is pulling the electron due to the minus I effect. You know the carbon over here is sp2, more electronegative as compared to the carbon with sp3 and all that. The phenyl group also shows minus I effect. Overall, since this is greater and this is smaller, overall it will be a weak electron donating group because of the cancellation of minus effect. It becomes weak electron donating group. So acidic nature will be less than formic but more than acetic acid. So we say in benzoic acid, the benzene ring gives electron, it gives electron due to resonance effect, and withdraw electron, also pull away the electron, withdraw electron due to minus I effect, withdraw electron due to minus I effect. So overall if you see, overall the benzene ring is weak electron donating group. And wherever you hear the word electron donating, the acidic nature will be less. So the order will be formic acid, then benzoic acid, and then acetic acid. Now lastly, let's compare the acidic nature of carboxylic acid and phenol. Let's see out of carboxylic acid and phenol, which is going to be a better acid. Already I have told you carboxylic acid is a stronger acid as compared to phenol. Already I have told you. And phenol, is more acidic as compared to alcohol. Carboxylic acid, because of its higher acidic nature, yesterday we have done, if you reacted with sodium bicarbonate and sodium carbonate, it gives you brisk effervescence. But in phenol, if you put sodium carbonate or bicarbonate, you don't get any brisk effervescence, because phenol is not so acidic that it will like to decompose bicarbonate or carbonate. So because of the difference in acidic nature, carboxylic acid gives the test with bicarbonate or carbonates, phenol doesn't give. Now coming back to the thing, that which is more acidic, carboxylic acid or phenol. So what we are going to do is that we are going to compare the stability of carboxylate ion, corresponding conjugate bases. We are going to compare the stability of the carboxylate ion with phenoxide ion. We are going to prove just now carboxylate ion is more stable as compared to phenoxide ion due to resonance. This is less resonance stabilized, this is more resonance stabilized. Because in this reaction the product is more stable, this will happen more towards right side. In this case the product is not that stable, so the reaction will not go in the forward direction so easily. So this reaction goes in the forward direction readily as compared to the phenol. Or we can say carboxylic acid H plus losing power is more as compared to nothing but phenol. So we say carboxylic acid is more acidic than phenol. Reason we are going to write down, but we are going to prove it also as carboxylate ion, the conjugate base of carboxylic ion. Carboxylate ion is more resonance stabilized, as compared to phenoxide ion, as compared to the phenoxide ion. Now we have to prove it why carboxylate ion is more stable as compared to the phenoxide ion. For that we need to draw their resonating structure. Carboxylate ion, the structures are equivalent. Apart from equivalent, what happens is the negative charge can spread on two oxygen atoms. Because it has got two oxygen atoms, on both of them the negative charge can spread. And if the negative charge can spread on more electronegative atoms, more number of electronegative atoms, the resonance stability is better. So negative charge can be present on this oxygen or on this oxygen. There are two oxygen on which it can spread. Whereas in the case of phenoxide ion, the resonating structures are not equivalent and the negative charge is localized only on one oxygen. Why it is so? Such a funny question, because in phenoxide ion we just have one oxygen. Can't help it. The God has not given him two oxygen to delocalize its negative charge. It is not his mistake. So because in phenoxide ion the negative charge is localized on one oxygen, that's why the stability is less. So phenoxide ion resonating structures stability is less because they are not equivalent, and the negative charge is present or localized only on one oxygen atom. So that's why it's comparatively less stable as compared to the carboxylate ion. If you remember, we have seen the resonating structure of phenoxyanion in the chapter called phenol. It's just a repetition that we are doing. So comparatively they are less stable as compared to the carboxylate ion. So we are just going to write down this, that why phenoxyanion is less stable as compared to the carboxylate ion. Two main reasons. And because carboxylate ion is more resonance stabilized as compared to phenoxide ion, that's why carboxylic acid is more acidic as compared to phenol. And you know, phenol is more acidic in comparison to the alcohol. So let's write down the carboxylate ion. The carboxylate ion is more resonance stabilized, as compared to phenoxide ion, Two reasons. Phenoxide ion, because, as I told you, because number one, in carboxylate ion, resonating structures are equivalent, they look alike, resonating structures are equivalent, and next, that in carboxylate ion, negative charge is spreading or delocalized. Carboxylate ion, the negative charge delocalized on two oxygen atom. Whereas in phenoxide ion, if you compare it with phenoxide ion, whereas in phenoxide ion, negative charge is localized on one oxygen atom. So before we close the topic, let us discuss two reasoning questions, and then the topic of carboxylic acid is over. One of the questions which I have taught you while I was discussing the acidic nature of carboxylic acid, the question is why carboxylic acid evolve carbon dioxide with the salt called sodium carbonate or sodium bicarbonate, but phenol does not. I told you this is due to the more acidic nature of carboxylic acid. It has been found that carboxylic acid is more acidic than the acid called carbonic acid, H2CO3. And these are the salts of carbonic acid. So since carboxylic acid is more acidic than carbonic acid, so they can decompose the salt of carbonic acid, that is sodium carbonate and sodium bicarbonate. Whereas phenol is less acidic. It is less acidic as compared to carbonic acid, H2CO3. So phenol is not able to decompose the salt of the carbonic acid, namely sodium carbonate and sodium bicarbonate. So phenol doesn't give the reaction with sodium bicarbonate and carbonate because of its lower acidic nature. So second question that we are going to discuss over here is that in carboxylic acid we have a carbon with a slightly positive charge. You can see oxygen is there, it will pull the electron like this. So this carbon has a positive charge. Still the carboxylic acid doesn't like to react with the nucleophile. No reaction with the nucleophile. The nucleophile will not be able to attack on the carbon of the carboxylic group. Why it is so? Why carboxylic acid does not undergo nucleophilic addition reaction? What's the problem with carboxylic acid? Doesn't react with the nucleophile, doesn't undergo nucleophilic addition reaction with the nucleophile. Even though there is a positive charge on the carbon, why it is not attracting the nucleophile? The reason is very simple. The positive charge over here that you are seeing is actually a chalawa, because this actually gets reduced to a higher extent. It is so much less, or the magnitude is so much less, that its attraction towards nucleophile will be very, very less. Who makes this positive charge less? You can see in carboxylic acid. Basically there is a resonance, and because of the resonance what happens is the positive charge on the carbon of the carboxylic group will get reduced. This is resonance, the electron is being given, so the positive charge will become less. It will become so less that its attraction with nucleophile will be very, very less. So we say due to resonance in carboxylic acid, due to resonance in carboxylic acid, due to resonance in carboxylic acid, the positive charge on the carbon of the carboxylic group, carbon of the carboxylic group is reduced, and attraction towards nucleophile will also be less, and attraction towards nucleophile is less. Attraction towards nucleophile is very, very less. So that's all for the carboxylic acid. Carboxylic acid is over. Happy holidays. Okay, enjoy yourself, study also. We'll be sending few videos during the vacation also, so we'll be sharing with you the practical work also. So keep utilizing your good time. Thank you. Have a nice day. Bye.